Well, this next topic is like improving guest latency throughput by improving the interaction of RCU in KVM. In this case, what we want is to run time-sensitive tasks with very low latency inside KVM guests. And the issue that we were perceiving is that we were having latency violations in cyclic test and OSLET that were caused by RCU-C threads running in the same CPU as the RT tasks. But, well, what is an RCU-C? This is the kind of bug that we had to deal with. You see that there are context switches between CPU and for the vCPU and the thread and the RCU-C, and then it goes back to the guest and you perceive a latency violation. The RCU-C thread, they run RCU core when it's necessary. When some time has passed and you haven't reported a quiescent state. I will go a little bit on that in the next slide. But the idea is that in RCU, if you don't report a quiescent state for every other CPU that may or may not be using that structure, you will end up getting a CPU stuck, that CPU that's waiting for the RCU to finish that operation, so it can like free the structure, the copy of the old copy, right? RCU is a very efficient parallel programming mechanism. In read, it does not use atomics or anything like that, and on write, you just have to ask for every other CPU to make kind of report they are not using our structure, which we call quiescent state. Once they all report it, you can go on with your processing. So if you do very little writes and use that data across many CPUs, it's a good way of protecting your data. When no CPU is, when your CPU is not referring or like trying to use any RCU protected memory, it's safe to be in quiescent state, as I mentioned before. The issue is that if a CPU stays too long without reporting a quiescent state, as I mentioned, that CPU can, the other CPU that's requested that grace period will be stuck. That's the case for the host, and that's the case also for the guest. And you can have a lot of latency on that workload, and that's not good. Well, let's say that you just entered the guest. You report a quiescent state, which is already happening. You run your guest for a long while because your vCPU is doing a lot of work. And at some point, the timer will just interrupt you and say, well, you need to report a quiescent state because I have another CPU there that's waiting for this. And then it reschedules out your vCPU and schedules in the RCU thread. If you end up to the timer interrupt and it asks for that. So one idea of doing this, of solving this, is that we report a quiescent state in the guest exit as well. So it saves most of the cases of like running RCU-C outside guest context, but it still happens. Then you just left the guest state. But there is a chance that after you just exited, you receive this request from another CPU from synchronized RCU, and when your timer interrupt happens to hit that part on its routine to check for RCU reporting, it will just run RCU-C anyway. So we have this suggestion to have this RCU patience, which will just act on RCU grace periods requested after some time, like some microseconds or some milliseconds. So the idea is that whenever we are just exiting a VM, we don't get hit by RCU-C unnecessarily, because it will just soon join enter the guest again and report quiescent state as well. So The idea is that we don't run RCU and we have more CPU time for our real-time workload. With those, we perceived a drastic reduction in the max latency on guest cyclic test. And as well, we perceived performance gain in the RT roast, even though it's marginal, it's something because you have more CPU time to your workload and less CPU time spent by the RCU at this point, because it's cheaper to report a quiescent state in guest exit where you are sure that you are in a quiescent state than reporting it with RCU thread, because you have to switch back to the guest. Sorry, you have to switch back to host and schedule a task for that. Thanks. What we also notice performance gain in non-RT hosts, which is quite significant. I mean, we noticed like 4.5% more CPU cycles that were used for that CPU, vCPU. So the guests run longer, 4.5% longer with those changes. So on top of improving the latency, it also improved around 5% of the CPU time available for VM, so you can perform more work at this point with the same machine, with the same VM, just by applying those changes, because you're running less RCU and you are having more time. And that's it. The commits that I mentioned just got merged, so very recently, so it's kind of merged, but I thought it was interesting to comment to you guys.
Well, right now it's break time, but I'll take one question if there is one. But not, yeah, I know everyone wants to go for the, oh wait, there's one question. Sorry guys.
Okay, so just for being sure, you didn't have any peak latency in this case where there were hundreds of milliseconds or so. You are just lowering the worst case scenario, but there was no problem with latencies, right? I mean, you didn't have, okay.
Yes. Yeah, we have this target of latency of like 40 microseconds, and when it went out to that, we reached it to try to fix the bug. I'm not sure I got your question correctly.
No, that if it was a worst case, maybe higher than what you achieve now, but there was no problem with having determinism before.
Oh no, I think it was a question that basically saying what was before you did the change, how bad it was before the change?
No, how bad, but that the worst case scenario before these changes was also known.
Yeah. The latency that I mentioned here is the worst case scenario. I mean, I run cyclic tests for like 24 hours and get the CPU that performs the worst, and that's the number that we have here. So it's the worst case. I mean, we can't lose a deadline. So if that one case we got a higher latency, we have to deal with that, right? Yeah.
Okay. Thank you.
Thanks, everyone.
And with that,